carrying out geophysical investigations for tunnels, reducing uncertainties and risk. He is also principal author of document titled Geophysical Investigations for Tunnels, published by Tunneling Association of India and Central Board of Irrigation and Power. Now I request Dr. Sanjay Rana to make the presentation. Over to you, sir.
Thank you very much for a liberal introduction. Just wanted to confirm with you, how much is the total time for this session?
It's approx for 50 to 1 hour, 50 minutes to 1 hour.
All right. Thank you. So what I'll do is I'll try to wrap up the presentation in something around 45 minutes, and then we can take questions immediately after that.
Sure, sure, sir.
Thank you. So I'm just putting a timer of 45 minutes here, and yeah, great. And I'll start sharing my screen now. Okay, just a quick confirmation. My screen is visible?
Yes, sir, it's very much visible.
And slides are changing?
Yes, sir.
Perfect. So thank you. First of all, thank you very much to the organizers for giving this opportunity to make this presentation on role of geophysical investigations for dam siting. And it's a very, very interesting topic and very close to my heart because of the importance it carries in the entire investigation protocol of constructing any new dam, or for that matter, any structure on the surface of the earth. And dam being a very, very huge mass which we are putting on the earth, so it becomes even more important. So topic is very close, and I hope you will enjoy this presentation. As I said, I'll try to finish 15 minutes before in the allotted time, so that we have at least 15 minutes for our discussions. I represent the company Parson Overseas Private Limited, which is an ISO company. And we are the largest engineering geophysics company in the country. But more than that, we are known for bringing new technologies in the country from time to time. Is starting from GPR in 96, and then shear wave refraction in 97, and the list goes on. So our emphasis is to bring latest and the cutting edge technology in the country, so that it can be used for various purposes in India. We are an Indian multinational, so we have office in India, which is in Delhi, Kolkata, and Bhopal, and we have 2 offices abroad, one in Bahrain and other in Saudi Arabia, and we are working in 18 countries around the world. Various prestigious projects which we have completed. 76 hydroelectric power project sites were investigated by us from 2001 to 2002, which was under 50,000 megawatt project of CEA. And Lower Subansiri was done by us, and so many hydropower projects which we have done over the period of time. I have been already introduced very liberally, so I'll not go into my introduction anymore, except for the fact that some time back, I also came up with guideline on geophysical investigation of dams, which was actually dealing with how existing dams should be investigated, other than the dam siting. But this particular presentation, I'm going to keep to dam siting only. But geophysics is used extensively also for investigating the existing dams. So that, of course, is a topic for some other presentation. So coming to the topic, when we talk about weak formations, we talk about difficult formations, we talk about design. The first thing which comes to mind is very famous quote by Shri Visvesvaraya, that engineers' first problem in any design situation is to discover what the problem really is. If we are able to find out what the real problem is, then design is something which can be done. Now, situation is that there are new tools which are available, which are becoming available from time to time as we are going through a phase of technological innovations. But for some reason, we say, like, someone offers us to these tools to us, tools are available, use them, don't be scared, your job is still safe. But we say, no, thanks, we are too busy. So the question is, are we too busy to improve? This applies to practically most of the investigation protocols we are still following, going by the same protocol, that is drilling, taking the core samples out, studying the core, and making our assumptions based on whatever limited data we get out of that. Now, the point is that difficult ground condition, when we talk about, and as the topic of this particular workshop also is about weak ground conditions. The difficult ground conditions or weak ground conditions, the fact is that expertise and engineering solutions are available for dealing with any or almost any ground condition. For example, there is a shear zone, there is a fracture zone, there is a weak ground. There are so many ground improvement techniques which can be applied to take care of such issues. The problem is meeting the unexpected. That is, we don't know what exactly we might come across as we are going through our process of construction, and that's where the problem is. So meeting the unexpected and uncertainty of the ground condition is the problem. So that's where geophysical investigation comes in picture, which I'm going to talk about. So what is geophysics? Just for the uninitiated people who have not come across geophysics ever, I would like to start with this particular slide. I think this is common to practically all the presentations I make in the field of geophysics for non-geophysicists, because this is the quickest and the fastest way to explain what we are doing. So on your screen, what you have now are different medical images. So you have, for example, ultrasound, you have X-ray, you have MRI, you have CT scan, different kind of images are there. What we are doing in this is we are sending different rays and waves inside the human body and reconstructing what is inside the human body by observing either the reflections or transmission of these rays and waves. What we are not doing here is invasion. That is, we are not cutting through the body. We are doing all this in a non-destructive manner without cutting the body. Now compare these images with the images on your screen now. This, for example, is a shear zone in an otherwise good bedrock. These are reinforcement bars in a concrete slab. These are buried pipes under various layers of road. This is a dam site which has been investigated to see the complete extent of rock. This is again a site which has been investigated to find out the shear wave velocities and where the low velocity medium is. So these are the results which are resultant of medical imaging, and here are the results which come from geophysics. So in geophysics also, what we are doing is we are using different kind of rays, waves, and fields to create an image of what is in the subsurface without drilling, without cutting. So that's the correlation which makes it very easy to understand what we are doing in geophysics. Now, these are the images of existing dams. As I said, we can use these methods for existing dams also. For example, this is a concrete dam, and here seismic tomography has been done to find out fracture zones between the downstream and upstream wall of a concrete dam. This is a Masonry Dam. This is very much from India. I don't name the dams, but again, upstream and downstream side, this section has been done, and we have been able to find out where exactly the bad zone is, right? So this is a density scale. So you can see the density in this area is much lower than the density in the remaining area of the dam. Similarly, this is again a dam. It's a complete L section. It's around 470 meters long dam. And this has been done from the dam top to the dam gallery. And now once we do it, we know exactly where the bad zones are. These green ones are the low velocity zones. So these are the bad zones. And this entire thing took 2 days of time. Okay, so entire investigation, this one takes around 2 days. This takes around half a day. So this is the speed, because again, it's like X-ray, it's like MRI. They're fast, they're quick, and non-invasive. Geophysics as a science is falling at the intersection of geology, physics, and maths or computer science. So this is where geophysics falls. And why use geophysics? The simple answer is, again, coming from your medical imaging example, that why you go for X-ray and ultrasound and MRI? Because why not to directly go to a doctor, ask him to cut open your body and check where the problem is? Because you do not want destructive investigations to be done unless you know exactly where destructive investigation should be done. So low cost, just like an X-ray is much cheaper than surgery. So similarly, geophysical investigations are much cheaper than any other investigations. Rapid coverage with airborne geophysics, you can actually cover thousands of kilometers in a single day. Continuous information. So look at the example here. There is a void here. There is some anthropological features here. There is some fossil here, and this is a limestone pinnacle. Now, if you're only relying on drilling, right, there is 1 in a million chance then you will hit these kind of isolated objects. But if you do a geophysical investigation, you will be practically able to map all these features, and then you can drill exactly where your anomaly is. So that's where optimization of drill holes comes. use of geophysics does not mean that you do not use borehole or you do not use the logging of your holes, right? Boreholes are important to determine certain properties which only can come from laboratory investigations. But idea is optimization of holes. So if you do a good geophysical campaign, instead of doing 100 holes, you can actually end up doing maybe 5 or 7, and still your information can be multiplied by 100. That is the whole idea, because it is giving continuous information. So minimization of surprises, and of course it is good for early stage application for better planning and smooth execution. Now, which method is to be chosen is an important point. If you choose a wrong method to do an investigation, it is actually worse than doing no investigation, because ultimately a wrong method will give you misleading information. So there are many factors which are to be considered when you choose the method. I will not go so much into detail of all this, but the idea is, for example, if you have a fracture, you go for X-ray, right? You have a tissue issue, you go for MRI. If you are having something where you need very detailed information, for example, scanning of your head, you go for CT scan. How are you choosing which method is good for which application? So it is depending on which physical property you want to see contrast in. For example, X-ray is very simple. Dense areas will block X-rays, non-dense areas will let them pass. So X-ray is good for that. So depending on which property is going to give you best contrast, you choose a particular method. Quick confirmation, Kalpana ji, my slides are moving, everything is fine?
Yes, sir.
Perfect, thank you. All right, so coming to advantage and limitations. Advantages, as I said, it's a rapid and cheap survey tool, easily integrated with other forms of ground survey. It's totally non-destructive, and modern processing methods give a visual image of the subsurface. So these are various advantages. There are limitations, of course. It can be ambiguous without controls. For example, if you are just doing one geophysical method and trying to interpret everything out of it, there can be ambiguity, there can be non-uniqueness. In few cases, resolution can be poor, discrimination can be poor, and then of course there can be noise, there can be artifacts. So that's where the experience of the practitioner comes in picture. The design of survey comes in picture, that you are not depending only on one method, you're having couple of methods in your toolkit to do what you want to achieve. Various methods are there, as I said, seismic methods which measure elastic wave velocity, GPR which measures EM pulse velocity, electromagnetic, DC resistivity is measuring resistivity, EM conductivity is electrical AC conductivity, magnetic is measuring the magnetic field strength which is being created by subsurface anomalies, gravity method is measuring gravity field strength which is directly related to the density of the material. So depending on what exactly is your objective, a method has to be chosen. And choice of the method is so critical that a wrongly designed geophysical program can result in complete failure. And that has happened in many projects. Over my last 32 years of practice, I have come across various clients talking about how they got some investigation done, but they did not get the desired results. And more often than not, it boils down to 90% the wrong choice of method, and then remaining 10%, of course, it is about the inefficiency of the person or the geophysicist who was doing the job, but mostly it is about the wrong choice of method. Return on investment, as I said, is very, very high on geophysics because it gives you detailed investigation of sites, saving huge costs towards change plans, project delays when surprises crop up, no drilling, no digging, so vast information at fraction of cost of traditional methods, and it is early stage application. I am talking about these methods since 1995 when I became an entrepreneur. Now, it has been quite a long journey, 26, 27 years. Thankfully, geophysics is being used more often than earlier in various applications, but still 80% of the calls which we get are firefighting calls. What I mean is firefighting calls is that something has gone wrong, and then they realize that, oh, we need more information here, so let's get some geophysics done because we heard Dr. Rana talking about it on this particular conference. Well, firefighting is not the right way of going about it. If you do it in the early stage, that is before you finalize your design or before you start your construction, and even before you do any drilling, and then do the drilling based on the results of geophysical investigation, That results in better planning and a smooth execution of the project. Now coming to dam site investigations. When we talk about dam site investigations, these are engineering structures constructed for different purposes. Like dams are made for irrigation, for power, for various purposes. They are of different sizes, shapes, and types. You can have, earth-filled dams, you can have concrete dams, you can have masonry dams. In all cases, many essential studies should be carried out before deciding the location, type, and size of the dam. Among those studies is a geological investigations which should be carried out to deduce the geological conditions in the most relevant site, depth of the foundation and their types, cutoff depth, types of the available construction material, and types of the expected geological hazards. So these are various objectives when we are talking of dam site investigations. Without proper geological investigations, the siting of a dam will cause serious hazards during construction and during commissioning of the dam. So geophysical methods provide direct answers and valuable additional data to augment other studies and more invasive means of evaluation such as drilling. I'll be showing you certain examples where number of drillings have been done because of non-continuous nature of drilling, you missed on certain features which could have been disastrous at a later date. So geological investigations for selecting and locating dam sites is one of the most significant studies which should be carried out in different scales and stages before deciding the best location for a dam. When we talk about best location, it just cannot be determined by the geomorphological conditions of the area. You have to do number of studies to decide what is the best location. Therefore, an adequate assessment of site geological and geotechnical conditions is one of the most significant aspects of dam safety evaluation. So this is objective, a very, very important objective. Evaluation of the safety of a new dam requires, among other things, that its site, abutments, foundations, and reservoirs have been adequately examined, explored, and investigated so that the geological conditions are fully understood as much as possible. So first objective, as we write, is the geology of the dam site, including the foundation for the dam itself and the sites for other structures such as spillway, diversion tunnels, and outlet works. Geology of all these components is very, very important to study. To check whether the dam foundation has sufficient strength and durability to support the type of dam proposed, whether the foundation is watertight, especially when calcified rocks occur in the site and in deeper horizons below the foundations. Second objective, the geology of the area to be occupied by the reservoir once the dam is completed. Whether the storage area is watertight or are there areas of cavernous limestone or gypsum which might lead to dam not retaining water. There are many projects where dam has been constructed, but at the end of it, dam doesn't retain any water because the reservoir area is not watertight. It is allowing the water to seep through. Then stability of the slopes of the dam site, the third objective. So stability of the slopes in the dam sites and reservoir area, whether landslides into the reservoirs are possible, which might cause a wave of water to be pushed over the top of the dam. There have been many dam failures where a huge landslide has basically created a wave which has overtopped the dam. So these kind of slope stability studies are important. Then finding source of the construction material, which will be needed to build a dam in nearby areas of the dam site, including all required types like aggregates of different types and sizes, filling material in the core and both surfaces. So this finding out the construction material is another objective, which again can be fulfilled by geophysical investigation. So all these objectives which I have talked about, if we start with a good planning and do good geophysical investigations, followed by optimized drilling, you can cut hugely on the amount of time and money which you spend on investigation and improve hugely on the amount of information which you're obtaining out of it. So necessary investigation steps, if you go right from the beginning to the end, study available geological maps, geological mapping, geophysical investigations, drilling, ideally with geophysical logging, then slope stability analysis, hydrogeological studies, seismicity studies, burrow area studies. So these are all part of investigations for a new dam site. So when we talk about geophysical investigations, There are different type of geophysical studies which should be performed in the dam site and the reservoir area to indicate, first of all, the groundwater level, mechanical properties of the rocks and the depth of the weathering zone, detect faults, fractures, shear zone, weak zone in the areas of interest, to investigate the burrow areas, to conduct slope stability studies, to determine shear wave velocity for seismic hazard studies. Okay, so all these studies of geophysics should be carried out on a new dam site. So today in this particular presentation, I'm going to cover a few of these methods, maybe 2 or 3 of these methods. It's a very, very detailed subject. And idea is just to leave the message here that when you are starting with study of a new site, which is to be used for something as important as a dam, it is good to be thorough. And when you want to be thorough, it has to start in a sequence. So you have to start with, study existing geology and then geological investigation. And the next logical step should be geophysics before you start any drilling, because geophysics has the potential of giving you continuous information of the entire site. So here, when we talk of advanced geophysics, because geophysics has been used around the world for a very, very long time, to be very honest, in India also, it's not that dam investigations have not used geophysics. It was not so popular, but even Chamera, for example, was geophysics was used. Tihri, we know very well, Russian scientists did a lot of geophysical studies there. So when we talk of advanced geophysics, what has changed over the time? Seismic refraction, for example, has given way to seismic refraction tomography. So seismic refraction tomography for bedrock profile, fault, fracture, shear zones. Resistivity imaging, or we also call it resistivity tomography, or electrical resistivity imaging and electrical resistivity tomography. It gives you detailed subsurface images even in velocity inversion zones. What is a velocity inversion zone? I'll talk about when I come to seismic refraction. But these are all limitations. So seismic refraction, for example, does not work in a velocity inversion zone. So there resistivity imaging comes to your rescue. REMI and MASW, which gives you shear wave profile from surface surveys without any boreholes. Okay, so this shear wave profiles are very, very important to understand soil stiffness and also to calculate the earthquake site hazard. So when we talk of seismicity hazard, that's where shear wave values are an input into the entire thing. Okay, so VS is very, very important. Then you have cross-hole, uphole, downhole surveys for P and S velocities for detailed analysis of various layers and dynamic modeling. So once you do this cross-hole, uphole, or downhole, you can find dynamic modeling, that is your bulk modulus, shear modulus, Poisson's ratio, etc., etc. Seismic reflection. If you're taking a tunnel, for example, for tunnel route investigation, seismic reflection is very useful. And then for powerhouse areas, electrical resistivity helps in earth grid design. So these are various methods which are useful for dam site investigation. I'll start with seismic refraction tomography. This is one of the most used method for most of the site investigation. I still always maintain that you should always without fail add another method with this. Never use any method in isolation is the message I always try to give to dam owners. And big examples are there from around the world. I will not name any dam, but one particular site is there in Bhutan where a seismic refraction study was done. It was done by some company from Japan, and they were not bad, like they were experienced guys. They did seismic refraction, and based on the P wave velocities, they they gave the depth of the bedrock, and based on, and then drilling was also done, and some samples were taken and bedrock was confirmed, and then started the excavation. And at that time it was realized that it was, if they had reported, let's say at 40 meters, the bedrock was not even encountered up to 70 meters. The thick boulder layer was misinterpreted based on P wave velocity as rock. Now that is the danger of using one single method. At the same site, for example, if you also use refraction microtremor or anything which is giving you shear wave velocity, you would have been very easily differentiated between the boulder layer and the rock, right? So that's why I'm saying, right as I'm showing this name, seismic refraction tomography, I'm also telling you the limitations of using a single method. But otherwise, it's a very, very strong method which is used frequently for dam investigation. The basic principle is very simple. You put geophones. Geophones are geo means earth and phone means listening. So they're devices which are listening to the earth. You put geophones all along the earth's surface, and then you start acoustic waves at one particular point. It can be done using a sledgehammer. If your depth of investigation is, let's say, 25, 30, 35 meters. If you want to go deeper, you have to use either a weight drop or an explosive. Okay, most of the dam sites are remote, so even explosive is not a problem, but you can otherwise use a weight drop. We have done hundreds and hundreds of projects in various dam sites, including 76 sites in Afghanistan itself, which I personally did myself, where there were a lot of problem by taking the drilling rigs there, and we use diffraction to find out the complete layering of bedrock. Anyway, so you start acoustic energy, it goes down wherever there is a change in the seismic velocity. The wave get refracted at one particular angle. There is critical refraction that takes place, that is r becomes 90 degrees, and it starts coming back to the surface, and these are refracted waves. I'm not going too much in theory of it, no intention of making you sleep in this after lunch session. So this is how geophones are put along a line, and this investigation is done. Now what is the result? That is important to understand. So this is what you get once you do this. So this again, as you can see, it's a valley formation here. So it's again a kind of a dam axis, and the refraction has been done. This is the elevation. So it's 880 to around 810 here. So it's 70 meters what you're seeing from top to bottom. And these are the velocities. Velocities are indicative of the mechanical strength of the rock. Okay, harder a rock is, higher is the velocity. If the rock is fractured, if the rock is having joints, etc., velocity comes lower. If it is overburdened, velocity is very, very low. If it is weathered rock, it is more than overburdened, but less than fresh rock. So there is an entire gradation of the velocity. So this is velocity, you can see. Okay. So here you can see these are the velocities which are more than 3,500 meter per second. So this is the bedrock. Remaining, this is the overburden, and all this is the weathered rock mass. So once you do this investigation, you are able to very quickly classify what is the depth of the bedrock, what is the thickness of the overburden, what is the thickness of weathered zone, etc., etc. So these are various examples where the borehole correlation also has been done. So this is overburden, you can see this is weathered rock, and this is the rock profile here. This is the rock profile. Various such examples. Okay. And what has changed over the years is that earlier we were doing seismic refraction, we were presenting layer-based models. Okay, layer 1, layer 2, layer 3, assuming that seismic velocity within a layer is remaining constant. That's not geologically true. The seismic velocity changes even within a layer. Seismic tomography has given us much better control over the way we look at the results, and we are able to interpret the results. So this is, for example, result of a typical layer-based model. So this was showing bedrock here, but now you see the rock is going down like this. So you are able to see with much more clarity how the rock is changing. This is the distance. So distance and depth. So this is 115 meters long profile, and the time which it takes to do this profile is around 1.5 hours. The time it takes to process this data is another 2 to 3 hours. So that is the speed of investigation, and this is the continuity of the information. So that is every inch practically you have the information available. Now look at this example. There is a small shear zone here. It's hardly 7 to 10 meters. Okay, what are the chances that you're actually going to detect this shear zone by a normal drilling campaign? 1 in 1,000 or 1 in a million maybe. Okay, but once you do a geophysical investigation, you're able to see that, okay, this is my rock, but this is where a shear zone is there, and now you can cater for it in your design. You can look for ways not to get affected by it when you actually start your construction. This is the interpretation. So once you have done the entire thing, you can see weathered bedrock. So this is how the weathered bedrock is. This is the overburden, and this is your very hard bedrock. And here you can see topography of the entire thing is clear. So it's not that you do a drill hole here and you do a drill hole here and then you connect it like this. That kind of interpolation or extrapolation always leads to error. What you need in such sensitive areas is continuous information. So you get this kind of continuous information, and that's the beauty of these methods. So what you get by seismic refraction is bedrock profile, rock quality and depth. thickness of overburden, fractures and weak zones, and used for slope stability studies also. So this is one of the method which is very, very potent to investigate your dam sites. Next method is electrical resistivity imaging. We also call it electrical resistivity tomography. Okay, because tomo is a slice, graphy is to write. So tomography is to write a slice. Whenever we are writing a slice of the earth, we call it tomography. So this is electrical resistivity imaging or electrical resistivity tomography. Here what we do is, it is based on a very old method of resistivity. Resistivity method says that if you pump current using two electrodes and measure potential using two other electrodes, then by Ohm's law you can find the resistance. Okay, so you are able to find out the resistance R is equal to V upon I, right? V is equal to IR. That's the Ohm's law. Now, same concept of the resistivity survey has been now used in resistivity imaging, where we put number of electrodes together. So these days, for example, I have the system. I started using with the 48 electrode system. I made my own actually at one time from my seismic refraction cable. That time electrical resistivity imaging systems were not commercially available. So I created my own with a switch box and all that. That's long back in '96. I used it for the first time on Kota Barrage for studying that Kota Barrage seepage. Anyway, that's history now. Now I have a system which has 120 electrodes. So you have multiple electrodes. You put them all in one line, and then you make different 4 electrodes current and potential, and that way you get a complete 2D image or a 3D image depending on what you're doing of the subsurface. So it's like this: you put electrodes and you see what is underground in terms of its resistivity. So in seismic refraction you are looking at P wave velocity, the compressional wave velocity, which is directly linked to the strength of the material. Okay, here you are getting resistivity, which is linked to the moisture content. Okay, so once you do this, for example, this is a rock. Again, the rock is having very, very high resistivity, so you will see high resistivity. Here are the tree roots, so you have low resistivity. So like this, you have a 2D resistivity section of the subsurface. So this is how you put it. All these electrodes in the ground, they're all connected by a multi core cable, and this is the kind of image ultimately which you get. So this is, again, you can see 1060 here and 860. So we, from here to here, we are having around 200 meters. And this was done in a very, very complex geology of JNK to find a exact location of a suspected shear zone. And you see it becomes very clear where the shear zone is located. So this is a very beautiful example of that. Again, this is rock, this all is rock, and here is a low resistivity zone which is starting from here. So it allows you to look in detail about your subsurface conditions based on contrast of resistivity. So seismic refraction based on contrast in strength, this based on contrast in resistivity. This is another example of from Lahaul Spiti Valley, where we did not have that by that time. These kind of resistivity meters with 120 electrodes and all that. Client wanted information up to around 500 meters deep. We made our own system of deriving information up to 450 meters. They had done number of drilling in this area. They were still not sure of the topography of bedrock, because as you can see, it is changing very quickly from one place to the other. So we did this investigation up to almost a depth of 400, 500 meters. The another example of detecting a cavity. So this was a water-filled cavity in otherwise good sandstone strata, where this was done to detect this cavity. So it's very good to detect zones with anomalies based on resistivity. Now this is a wonderful example. This again comes from a project which we did in it was in Himachal or it was in Lahaul Spiti Valley. Now I forget. It was very, very old. It's a very old project. Seismic refraction was done. As you can see, this is all bedrock. Now seismic refraction is working on the principle of Snell's law. Sin I upon sin R is V1 upon V2. If V2 is greater than V1, then R2 is greater than R1, and the critical refraction can only happen when the velocity of the lower layer is higher than the velocity of the upper layer. If a low velocity zone is coming under a high velocity zone, seismic refraction will not detect it. And that is why I said we always advocate to combine the method. So in this case also the method was combined. We did refraction, we did ERI also. And in ERI, a zone under a rock, it is possible because of tectonic activity, because of folding, was detected using electrical resistivity imaging. So this is a very strong case why methods should be combined to do a thorough investigation. It can detect your boulders. This is zone of water accumulation, various boulders. So detailed information you can get. It is also used, for example, for tunnel route studies. So this is a tunnel route, and here is a low resistivity zone, which was further investigated by drilling. And this is basically a fracture, a fault zone. Okay, here again, the weak zone is here. Best part is that all these methods now we have kind of mastered to do it across flowing rivers. So when you are finalizing your dam access, it is always a good idea to do a good geophysical investigation. Recently, for example, we have conducted number of river crossing studies, but these were for pipeline. They were taking the pipeline across the river and they wanted to find out what's the geology, and we did geophysics across that. For hydropower projects also, this one, for example, comes from a hydropower project in Nepal. This was the first which we did for river crossing. It was in 2001, so almost 21 years back. And you're able to do resistivity imaging, and this is, for example, all water area, and this is your bedrock. So you can see very quickly, like this entire investigation took around 1 day. In 1 day, you are able to do the entire axis. Just by putting a pontoon there, it takes some time, weeks and months, and then drilling in the water. And it's much easier to do these kind of investigation for your bedrock studies. Again, this is from a project in Arunachal Pradesh across river. So this was the river water. And you can see very clearly how the bedrock profile has been determined. This yellow line is basically the bedrock profile. So very, very quick methods to do this. This is one of a very good example where across this axis there were a number of drill holes which already had been done. Okay, so this was almost finalized as a dam axis, and we happened to be there in the vicinity, and we were asked to do this investigation. And so, for example, this is rock line. This yellow one is a rock line. So number of holes had been drilled and the rock was confirmed. And once we did this, we found the shear zone sitting right across it. And then, of course, further investigations was done, and this shear zone actually was identified there. Then, of course, it was correlated even with the existing geological maps. That's all a separate story. But this was detected. Now imagine you finalize this as a dam axis, you bring your construction crew, you bring your construction machinery, and then you come across these kind of anomaly. Imagine the kind of problem and the time and cost delay you're going to face at that time. All right. So these are various examples I wanted to show you. Next method I'm going to talk about is Remy refraction microtremor, or MASW. Now, in many cases, we want to find out the shear wave velocity. Those who are involved in the designs will already know that when it comes to seeing the earthquake hazard response, or vibration response, or liquefaction analysis, you need shear wave velocity. Okay, so for shear wave velocity, Remy or MASW gives a very quick way of finding it out. It is based on dispersion of Rayleigh waves, and once you do this, you are able to see very clearly. So this is, for example, 100 meters depth. This is the bedrock. This red one is the bedrock here. And here you can see this is a low velocity of low shear wave velocities which have been detected here. Okay, so it is very, very quickly able to give you the profile of the shear wave velocity. You can also find out VS30. Now VS30 is something which is used in the calculations of what all I said in hazard mapping, etc., etc. You can quickly find out VS30 also. Again, another example of Remy, 80, this is 100 meters depth, this is 80 meters, bedrock is here, and again you can see the change in the shear wave velocity with depth, and the zones with low shear wave velocity, which obviously are the problematic zones. So this has lots of application. We have done it in hundreds of projects. It is used for cavity detection also. It is used for site classification also. We also have done it for Statue of Unity, a number of projects. MASW is becoming very, very popular these days for various investigations. This is another example of Remy. where again, this is only 45 meters, but you're able to see various blocks of anomalies. Now, this is a combination of GPR profile. GPR is another method I'm not covering in this particular presentation because, it becomes just too lengthy and too many methods. But GPR is working on the principle of EM reflection. So when we are talking of high resolution shallow studies, GPR is the method to go for. But this is just to show you how different methods can be put together to make a model of the subsurface. So this is, for example, MASW, this is GPR, and then ultimately based on all the results, we are able to make a geological model. This is red soil, then weathered rock, then fresh rock. So this is how you have to, because GPR has a very high resolution in the shallow part of it. Okay, so it can detect even things of centimeters dimension. So very high resolution GPR has to be done. Combine it with but GPR only gives you interfaces. It doesn't give you property of the material. So combined with MASW, you are able to map the interfaces very accurately and then put property. So soil, because 250 meter per second VS, weathered rock because VS is 600, rock 1200, and fresh rock 2000. So all these values are anyway in the standards and codes. You can see these values which correspond to what. Similarly, ERI, MASW, and SRT, three methods have been put together to find out anomalous zone. Okay, so this is the anomalous zone: high resistivity, high velocity in MASW, high velocity in SRT, high P wave velocity, high shear wave velocity, and high resistivity. So this is how, once you put number of methods together, you remove the ambiguity, you remove the non-uniqueness, and you are able to make the results unique. Again here, the example of MASW. So these 30 meters here. If you are going up to 30, 35, 40 meters, MASW is something which we use. When we go more than 30, 40 meters, we have to go for passive source. So either you can use passive MASW or you can use REMI, refraction microtremor. Okay. This is again detection of a subsurface fault. So this is a fault here. This is the main fault, and it has been detected very nicely using MASW. So these are just examples to show how well we are able to detect the change in the geology once we are doing this. Number of examples. It is used, as I said, a lot for the cavity detection. So it has been used for cavity detection, weak zones, etc., etc. Next method I'm going to talk quickly about is seismic tomography. Again, a very interesting method. Once you want to investigate a subsurface in great detail, you can have two boreholes, and in between two boreholes you can conduct seismic tomography. So in this, we are sending rays from one to the other, and crisscrossing of these ray paths is being done. And then once we do the inversion of this entire thing, we are able to find out in great detail what is happening between the two boreholes. Okay, so now no interpolation is required. You know exactly what is happening between the two boreholes. This is an example of existing dam. So as I said, this is the L section, so dam top, and this is the gallery. And once you do the inversion, you see what's happening between the two faces. So this is the example I had shown that time, so you know exactly where your weak zones are. Again, dam upstream and downstream, crisscrossing of the ray paths. Again, you do the inversion and you know exactly where the bad zone is. So now once you're going for treatment, you don't need to plan from top to bottom. You know exactly where the bad zone is, so you can only treat that. If you do it for the new site investigation, so for example, S1, S2, S3, S4, S5, 5 boreholes are there, and tomography has been done between the boreholes. Now you are able to find exactly how different formations are going from one place to the other, and more importantly, detect features like this fault. This fault will not be detected just by drilling, but once you do tomography, you are able to detect this fault. So if you are having a drilling campaign, include seismic tomography in the drilling campaign and you can get much better results. Again, various boreholes in between seismic tomography, and now you have continuous picture. No interpolation is required. These are examples of a cavity detection using tomography. It's on 250 meters deep boreholes, and the cavities were detected using tomography. Distance between borehole here was as high as 110 meters, and this cavity was as high as 85 by 60 meters. And these were inclined boreholes because there was the platform available for drilling was very small, and this cavity was to be mapped by seismic tomography. There are various other applicable methods like seismic reflection, GPR, gravity and microgravity. I'm not able to cover these methods now, but idea is the message is that various methods are existing to give you insight into subsurface. And again, to conclude with where I started, why use geophysics? Low cost, rapid coverage, continuous information, optimization of drill holes, minimization of surprises, and always good for early stage application for better planning and smooth execution. So thank you very much for your time. I'm left with 37 seconds now. So these are the contact details. If you need any of these geophysical investigations for any of your projects, you can contact at this email ID, akaushik@parson.biz. For any technical clarification, I'm always there, sanjay@parson.biz. Please feel free to write to me, call me. My contact details are very much available with the organizers. So it will always be a pleasure to interact with you. This is my phone number and this is my email ID. Please feel free to take a note of this so that whenever you are looking in terms of subsurface investigation, it's always a pleasure to give whatever suggestions based on my 31, 32 years of experience. And it's always a pleasure to interact with fellow professionals. Thank you very much for your attention. And with this, I will stop sharing my screen and we'll take questions.
Thank you, sir, for making an excellent and detailed presentation on geophysical investigation for dam sites. May I now request to the participants if they have any questions, they may ask, please.
Hello. Hello.
Yes, sir.
Hello. Hello.
Yes, sir.
You are audible.
You are audible.
Thank you, Madam Ji. I want my request is that there are already mentioned by Dr. Sanjay Rana sir about electrical resistivity method. But apart of that, there are several methods of geophysical investigation, and mostly used for dam site investigation are these both method, seismic method and electrical resistive method. Now I want please throw light on the seismic method about dam site investigation, for dam site investigation. I request is that they kindly throw light on this method. And my next another question is that how we are able to detect and locate all the faults and plane of contact and probable depth to which the foundation of dam have to be made. Thank you, madam.
Thank you for your question. Like I basically started my discussion with the seismic refraction method, and I came to electrical resistivity method at number 2. So seismic refraction, electrical resistivity, MASW, and seismic tomography are the 4 methods which I have covered in this short presentation. So I am not able to understand what exactly you want to ask about the seismic method, because I have covered 2 seismic methods. One is for P wave velocity, that is seismic refraction, and second one is for shear wave velocity, that is REMI or MASW.
Okay, sir. But sir, how we locate and fault? How we able to detect and locate all the parts and plane of contact and probable depth to which the foundation of dam have to be made?
Right, that's what I'm saying. If you are doing an integrated geophysical exploration program, like I said, if you are starting with seismic refraction, now seismic refraction is giving you the depth of your various interfaces practically at every geophone position. Now what happens across a fault? When there is a fault, for example, there is a movement and the high velocity layer, for example, is going to shift down, okay, with respect to where it should have been if the faulting was not there. So this kind of change in the velocity depth, the depth of these layers, is detected very easily by seismic refraction. So that is what you can start with. You can start with a good comprehensive investigation using seismic refraction, using ERI, using MASW. At a later stage, if you are going for drilling, do seismic tomography between your drill holes, like I had shown one example, and you're able to very clearly see a fault location. So combination of the methods have to be worked out based on your site condition, where your dam is located, and it is obvious it is the most comprehensive way of doing your dam site investigation.
Okay, sir. Thank you, sir.
Thank you.
Do we have any more questions?
Even if we don't have any question right now, my request would be that please note down my email ID, which I had shown you. If you don't have it, please request the organizers to share it with you. And feel free to write to me anytime when you come across any problem. But if you have a question now, it will be a pleasure to reply to that.
If the participant want to ask the question on a later stage, they can write directly to the speaker or to us. We will arrange the answer and get back to you over the email. So I think we don't have any more questions right now.
Right. So just for benefit of audience, this is my email ID, sanjay@parson.biz. Please take a note of this. And at any point of time, you can write to me or, of course, write to CBIP. We are in regular touch and we will get back to you. Thank you very much. Thank you, Kalpana ji.
Thank you, sir. I would like to convey my special thanks to the speaker, Dr. Sanjay Rana, for sparing his valuable time for conducting this virtual session. Thank you, sir. Thank you once again and have a good day. Thank you. Ladies and gentlemen, now may I invite today's next resource speaker, Dr. D.A. Subramaniam, for making the presentation. Let me introduce briefly about the speaker. Dr. D.A. Subramaniam, presently head of the Department for Geotechnical Engineering Division at National Institute of Rock Mechanics, NIRM. He worked for 7 years in granite and cement industries in various capacities prior to joining NIRM in 1997. He is associated mainly with the geotechnical studies of many important engineering projects in the Himalayan region and presently responsible for planning, programming, implementation, and monitoring of engineering, geological, geotechnical investigations of hydropower projects, communication projects, underground storage plants, underground mines, and irrigation projects in India and abroad. He has established an innovative techniques for conducting in situ stress measurements in fractured and porous rocks, for which he got the patent rights from Controller General Patents and Design India. He is having the credit of preparing the stress map of India for contributing to World Stress Map. He's authored more than 70 papers to his credit, published in national and international journals and proceedings, and nearly 160 technical reports and 5 research projects submitted for various assignments. He is editor for 7 international journals and reviewer for various national and international magazines. Now I request Dr. D.A. Subramaniam to make the presentation. Over to you, sir.
Thank you, madam. No, not that.
So, do you want us to play the PPT on your behalf, or you would be running the presentation your own?
I'm doing it, madam. I'm just going to.
Okay, sir. Yeah, please.
This one here. This. Share. Window. Right. Am I audible, madam?
Yes.
My screen.
Even your screen is also visible. Yes.
Yeah. Okay, madam. Thank you very much for the nice introduction. And namaskar. Good afternoon, everyone. And today I'm going to talk about the ground stress, its measures, and applications in rock engineering. So, as introduced by Madam, I'm Dr. D.S. Subramaniam, and I'm scientist and head of the department, Geotechnical Engineering Division, National Institute of Rock Mechanics, Bangalore. Just briefly to introduce what we have done in NIRM for the last 33 years, just one or two slides I would like to share with you. These stress measurements we have conducted at nearly 200 project sites in various Himalayan areas for hydroelectric projects, crude storage plants, and irrigation projects, and other underground caverns. And we obtained 2 patents for stress measurements in fractured and porous rocks. And we have prepared the stress map of India for contribution to world stress map. Recently, we have introduced an online app for stress measurements also. And nearly 100 publications in various journals and 2 books are published regarding the stress measurements. And these stress measurements we have conducted at the maximum depth of 350 meters from surface at Himalayan regions of hydroelectric projects. And recently, we have conducted 600 meters also, 600 to 700 meters from surface at coal mines, which is first time in India. So this is the stress map of India we have prepared. From various sites, we have collected the data where we have conducted exactly the stress measurements, and we have mapped on Indian map, and we have contributed to world stress map. It has been recently incorporated in world stress map. And now my topic is state of ground stress, its use and measurement in rock engineering. So I'm going to talk about first the in situ stress. What is in situ stress? Why it is called stress? Actually, there are 2 types of stresses in the nature. One is physical stress and another is mental stress. Physical stress is applicable for the movable and immovable things, living and non-living things, but mental stress is applicable only related to human beings. These 2 stresses we have to be released. These stresses to be released as much as possible. Otherwise, there will be instability exists. So, as far as the physical stress is concerned, okay, Earth itself is having some stress. Consequently, all naturally formed formations like mountains, landscapes, and everything is having some stress. Since we are mainly talking about concerned with rock masses in the present context, stress may be defined as, in general, as the force per unit area. It is called force per unit area. And rock masses are initially stressed in their natural state. And whether one is interested in the formation of geological structures like folds, faults, or intrusions, and stability of artificial structures like tunnels, caverns, etc., stress is the most important factor. And the knowledge of in situ stress is the main key element in the process of design of any underground excavations. No matter what type of rock failure occurs, it is ultimately related to the stress change around the rock mass. So we have already told that force acting on a unit area of rock, that is force per unit area, can be expressed as a pounds per square inch or kilograms per square centimeter or MPa, megapascals. Normal stress, that is stresses acting perpendicular to the surface, and shear stress acting parallel to the surface. Actually, what is the origin of the stress? If we just go into the history, previously people used to think that weight of the overlying rock mass was recognized for more than a century as a primary source of stress around underground openings. But he postulated that is called, people used to think it is hydrostatic stress. That means like a water. Water is having the uniformly in all directions, the stresses are same. Like that, it is called hydrostatic stress, similar to the stress state in the liquids. This theory was later modified by him as a lithostatic stress field theory, which assumes the rocks in the crust are in the state of isotropic state. That means sigma maximum principal stress and minimum principal stress and vertical stress. These 3 components are same and equal. And for the long time, for many years, the design of underground excavations are based on predominantly on this concept. But the lithostatic stress field theory was later replaced by uniaxial strain model by Terjagi. This is in the year 1952, I think. This concept suggests that because rocks are confined at depth, the horizontal expansion is restricted by adjacent rocks. So that ideally the principal strains are becoming zero, thus making the horizontal stress is a function of the weight of the overburden and the Poisson's ratio. So that is called sigma h is sigma capital so small h is equal to vertical stress into Poisson's ratio V by 1 minus V, where P rho is that vertical stress is again is rho gh, density of the rock mass, and G is acceleration due to gravity, and V is the Poisson's ratio, and Z is the depth of the point of interest. So while this estimation was often sufficient for underground design purposes, it was noticed that the horizontal stresses frequently exceed the vertical stress in many cases, because of late, the introduced by Wegener, the continental drift theory, he proposed in many cases horizontal stresses are more because of the tectonic movements. So later people realized that horizontal stress is sometimes exceeding 1.3 to 1.5 times also, sometimes 3 times also, it's exceeding. So this theory again, Chauvet and all, they have proposed another theory that suggests a relatively straightforward exercise to estimate the value of in situ stress. However, Chauvet has failed to recognize that rock masses are heterogeneous and discontinuous characteristics that complicate the task of estimating the in situ stresses acting at a point. So whatever it may be the case, in recent years, numerical modeling techniques have been developed to help understand and explain the observation in complex stress regimes and for prediction of stress away from local point of measurements. The measurement of in situ stress is the most important criteria for the design of any underground cavern or underground storage plant or any structures. So this is explained. So whatever it may be the case, there are two main factors for the formation of the stress in the universe. That is, number one is gravity and another is tectonics. Gravity is nothing but vertical stress. Tectonics always related to with the horizontal stress movements. These are the main important factors for the formation of stress in this universe. So stress is fundamental to the principles and applications of rock mechanics. It is a tensor. It is a quantity with magnitude, direction, and the plane under consideration. Example of tensors are stress. It is defined at a point and represented by second order Cartesian tensor with 6 components. And it is always called, it is continuum mechanics, that each and every particle in the body is continually distributed, not like discrete particles. And it is a fictitious quantity that cannot be measured directly. So if you want to measure the stress, means you have to disturb the rock. Otherwise, you can't measure. So the total stress field acting in a rock can be represented by 3 components, S1, S2, S3, or sigma capital H, sigma small h, or sigma v, like that. Right angles to each other. It is common practice to consider that normally the ratio of the average horizontal stress to the vertical stress is denoted by K. K is the vertical horizontal stress by vertical stress. Based on the K, many design parameters are formulated. And the designs for the cavern design and all, K is the most important factor. And this vertical stress, maximum principal horizontal, vertical stress is always calculated. In some cases, it is measured directly in some of the methods, which I will explain you in the later slides. Otherwise, vertical stress can be, I have already told, will be calculated like rho gh density and rock cover and the acceleration due to gravity. And maximum principal horizontal stress should be measured, and minimum principal horizontal stress also should be measured. And there are 2 types of stresses. I already explained, that physical and mental. And this is regional and local stresses. Suppose if any focal mechanism data is available, there was a large earthquake and all, then we can get some stress data which shows the horizontal principal stress direction, but it is in regional in nature. But if you want to have the stress data locally, that means to design any hydraulic project, powerhouse, or any cavern, or any structure, then you should not depend upon the focal mechanism data, and you have to concentrate on the local stress. That means in situ, directly you have to go to the field and measure the in situ stress. So on real or imaginary plane through a material, there can be normal forces and shear forces. These forces create the stress tensor. The normal and shear stress components are the normal and shear forces per unit area. If you see here, normal for each, suppose if a cube is there are 3 stresses acting vertically, horizontally, and 3 directions. And along with that, shear forces are also acting at a point in the rock mass, are represented by 3 normal stresses and 6 shear stresses. So usually there are 9 stresses components acting in 3 directions on 3 planes. However, if the planes where the stresses act on the rotated, there is a position that the magnitude of shear stresses will become 0. It is a matrix. Everybody can understand, I hope. Hence, the stresses acting on the 3 planes are only normal stresses. In this situation, the 3 normal stresses are termed as principal stresses. That means vertical stress, maximum principal stress, and minimum principal stress. So, what is in situ stress means? In situ, why I am calling means, in situ means total stress. In situ boundary conditions we have to take into the consideration, intact rock or any water flow or any discontinuities or near the excavation and all boundary conditions we have to study. Then total stress we have to measure, that is called in situ stress. We have to go to the directly site and measure the stress, that is in situ stress. Suppose what are the types of stresses? The confining stress is there, stress is equal from all directions, and tensional stresses, that means pulling apart, and compressive stresses, that means pushing, that you compress, and shear stress, pulling apart, that is. So that is as parallel to a surface leads to change in shape, that is shear. And stresses acts perpendicular to and towards a plane is squeeze rocks may decrease the volume, and tensional forces away from a plane and pulls the rock apart. And there are various types of stresses, that is in situ, it is virgin stress, that means natural state in the stress which exists prior to engineering. The induced stresses are the natural stress state as perturbed by engineering. Suppose if any mining activity, any drilling, pumping, injection, applied load, swelling, etc., these are all man-made. So these are called induced stresses. And gravitational stress is the stress state caused by the weight of the overburden. I already told you vertical stress. And the tectonic stress is the stress state caused by tectonic plate movement. And the residual stress, the stress state caused by previous tectonic activity. And the terrestrial stress, and because of the moon activity and all terrestrial stresses will happen, seasonal temperature variation, moon pull, etc. Residual stresses because of metamorphism, magma cooling, changes in pore pressure, etc. And paleo stress is one type of variety that the previous natural state that is no longer existing. That means some of paleo stress means because of the joints, because of the fault planes and all these things, we can measure this. So that the paleo stress, once upon a time it was existing, that no more it is active. And near field stress means the stress state that in the region of an engineering perturbation. And far field stress means the stress state beyond the near field. And local stress, which is very, very important, the stress state in a region of interest where you want to construct a cavern or any structure. So that's why to study stress, the study of rock behavior in the solid state under varying environmental and internal conditions. Main focus how rocks are respond to applied stresses or plate tectonic movement to decipher the plate tectonic movement and mantle convention and gravity and diabatic movements, magma and all. For all these things also academically, these stresses are very important to know. And in hydroelectric projects, in underground mines, railway tunnels, irrigation projects, crude storage plants, nuclear plants, and all these major areas where we have to go there and measure the stress for the construction of any cavern and all. That I will explain you in later slide, how we will orient the caverns and all, everything. So in civil engineering, the stability of structures, orientation of tunnels, designs of caverns, etc., very important based on the design of the stress. And in underground mines, for design and orienting mine excavation geometries, overall mine stability and layout. In petroleum industry, knowledge of stress is important for the fracturing of formations to enhance the production of oil and gas. These in situ stress parameters are very much important. So why study stress? So I already explained, there is pre-existing stress state in the ground, which is a major contribution of the major geological phenomena of the earth. Knowledge of the state of stress can help in profitable exploitation of the natural wealth and disaster management. In civil and mining engineering, in-situ stresses control the distribution and magnitude of the stresses around underground openings. This is because rock which previously contained stresses, already rock is having stress. Now you are opening a cavern, you are making a tunnel. That means you are again disturbing the rock. That means it is having stress, and redistribution of the stresses will take place. So that is the reason knowledge of the state of present level of the stress is required to understand the impact of stresses on the excavations. Stress concentrations can create excessive deformation also, ground subsidence also, and failure of rock mass also. This basic knowledge of the stress state can help us in the safe and optimum design of any excavations. So in what way geologists are getting benefited to understand the mechanism of plate movement? Suppose our Indian plate is moving towards northeast direction, north 23 degrees, because we have conducted many stress measurements in India, almost 240 areas to 300 stress points we are having. We have prepared a map. We have come to a conclusion that Indian plate, already it is established truth that Indian plate is moving towards northeast direction, but the direction is not 22-30 degrees. And dynamic faulting. So how the faults are formed because of the stress release, and mountain building and the basin formations and earthquakes, it is release of the stress again. And other geological features like folds and other dikes and seals, all these are in one way, other way, it is related to stress only. So geologists should learn what is in situ stress, how it is acting, how these geological formations are formed. If you want to know, you have to know the stress conditions in the present area. Suppose in hydraulic projects, the powerhouse, it is existing inside the rock mass. So this powerhouse, it is a thumb rule, should be oriented along the maximum principal stress direction only. The long axis of the powerhouse should always orient along the maximum principal stress direction only. Otherwise, it will collapse. So how the maximum principal stress direction means, we have to measure the in-situ stress, and we will give the magnitude and direction of the orientation of the stress. Then accordingly, because so many projects in India, almost 180 project sites we have investigated, and we have given the direction, all these powerhouses and all, exactly they have constructed according to the direction which we have already given to them. Suppose if I say north 60 degrees, that means north 60 degrees east or west, anything, they have to construct plus or minus deviation 10 degrees, 15 degrees is okay. But major portion, major long axis of the powerhouse or cavern, whether it is powerhouse or shaft, anything, you have to construct according to the orientation, whatever we give, because we measure the stress and we give the particular orientation. Otherwise, if you deviate more than 30 degrees, 40 degrees means definitely it will collapse. So for transportation tunnels, how the circular tunnels, why the horseshoe shaped tunnel, and all these tunnels and all, it depends upon the stress direction, stress magnitude. So if vertical stress is more means the span should be very less and vertical roof should be high. If the circular, if weak rock conditions are there means the circular tunnel is the best. Otherwise, there will be a stress in the area where the floor and the wall meets at the particular point, the high horizontal stresses will be there. So to avoid that, if you make the circular tunnel, it will be stable. So horseshoe shaped tunnel for good quality of rock, and circular shape of tunnel for poor quality of the rock. And in irrigation projects, you have the almost 10 to 15 areas we have conducted in Telangana area, Telangana state, in Pranahita, Chevella, Kaleswaram, and other underground irrigation packages. The pump house of the project, that is the main key. That pump house should be oriented along with the major principal stress direction. That means maximum principal stress direction, orientation, the long axis should be aligned. So in mining industry, the knowledge of rock mechanics can be utilized for the high horizontal values have a profound influence. The room and pillar mining, or if it is a long wall or anything, stresses in pillars affect the overall mine extraction ratio and control the overall mine stability and layout. How? Earlier people used to think, if I already told in long back, if vertical stress is more, because of that roof is getting collapsed. That is wrong. Suppose if there is a balloon, if you press vertically, the which direction that it bulges in horizontal direction. That means if vertical stress is more, there will be a problem in the walls. If there is a horizontal stress is more, suppose again, balloon, if you press horizontally, it will bulge towards vertical direction. That means roof will have some problem. This recently, in 1960s and 70s, people came to know by extensive research. Because of the vertical stress, the walls will have problem. Because of high horizontal stress, roof will have some problem. So how to avoid all these problems means we have to measure the in situ stress. So here you see horizontal stresses are more. That means roof shear and buckling is taking place. High horizontal stresses, the overall stability of the coal, mine roadways and haulage roads, wherever you see, these stresses are very much important to avoid all these roof shear and buckling problems and floor heave problems. So mine roadways oriented across the nation, what will be happen? The major horizontal stress may severe roof falls will experience, and stresses are found to be redistributed due to local tectonics and mine openings. I already told, rocks are initially stressed. If you are opening in the mine, the stresses will be redistributed. And again, after opening, there you have to measure the stress. What is the present level of the stress, magnitude and direction? According to that, you can't reorient everything in the underground mine. It is practically not feasible also. But numerical analysis and all will help us. At least something we can orient mine roadways and other haulage roads and everything. At least some dangerous things and all we can avoid. At least roof collapse and all. So at least it will give the data to how to address the stress problems and all. So rational design of the mines, these in-situ stress parameters are very much important. So for crude storage petroleum industry, I already told for the enhancing the production of the oil, this crude storage and all these stress parameters are important. But in this underground this gas storage, the stress parameters play a vital role, because the minimum principal stress magnitude should be more than the liquid pressure in the gases pressure. Otherwise, if it is less, the gases will escape. So that is the thumb rule, that minimum principal stress should be more than the water pressure. So that then only these gases and all will stable. So the principle behind the soil and underground rock cavern essentially implies groundwater pressure for containing the oil and gas within an unlined rock cavern. It is lined or unlined. If it is unlined, means the function of hydro confinement is to provide an artificial water recharge in the rock mass in order to enhance water flow patterns and maintain the groundwater pressure in the fissures above the storage cavern vicinity. So the water pressure should be high enough to prevent gas from leakage out from the cavern. How we will come to know? Because we have to measure the stress and find out the magnitude of the stress. Then only we can give the design. So suppose in nuclear repository sites, the storage sites always, because nowadays nuclear wastage, it is because we are constructing here in Karnataka, in Andhra, and many areas in Visakhapatnam area and other areas to just throw the nuclear waste. So for the nuclear waste, it is very, very deep constructions, maybe 500 meters, 600 meters like that. So that caverns, that nuclear waste disposable areas should be very safe. For the at least 100 years, 200 years, it should be safe. So for that, radioactive waste cancistors will be oriented along the maximum principal horizontal stress direction only. The storage sites always parallel to maximum principal stress. Of course, opposite to the placement routes, you can just parallel to minimum principal stress direction. So major factors, what are affecting the ground stress? That is effect of depth, effect of topography, effect of geological structures. So what is the effect of depth means? Always this vertical stress always increase, because it is, if it is rock cover is 100 meters, means approximately it is 2.7 MPa. That means density of rock, acceleration due to gravity, and height of the rock of the overburden. Roughly for 100 meters, it is 2.7 MPa. For 200 meters, 5.2. Like that, it is calculated. Always a Roji, this is calculated. Some overpouring technique is there, which I will explain you. You can measure the vertical stress also, not like calculation. So this vertical stress always, it is linear to the depth. The vertical stress against the below zone, if you go on deep and deep, it is a fraction 0.027 Z. Always it will be increasing. So the average horizontal stress to vertical stress, the K already told, it is very important factor for the design of any caverns and all. K is always 1 times, 2 times, 1.3, 1.5, 2 times, like that. Based on the K only, we have to design the rock structures and underground caverns. So in topography, how will it affect? Suppose if any topography is there and river is there, on the river edge side or in the valley side, if you want to construct a project, near horizontal ground, the principal stress directions are always changing. Principal stress, if you measure in the valley portion of the area, this automatically, the stress will take the direction of the valley automatically. So that is the main important factor. The influence of topography is always there. Wherever there is, whenever we go to site, first of all, we will see where to measure. Then they will see any topography effect is there or not. Topography effect is there means we have to go away from the little bit the valley side and measure the virgin stress. If you measure near valley portion means automatically stress will take its direction. That means influence of topography on initial stresses, it is always there. Beneath the valley, one more thing, high horizontal stresses will be concentrated. This is the thumb power rule, that horizontal beneath valley side, one principal stress is normal to the slope and equals 0, while other two principal stresses lie in the plane of slope beneath the sharp note of a V-shaped valley. The institute stresses are very high at the bottom of the valley always. So this practically we proved, we have measured in one of the projects in Ropali Ghat hydroelectric project Nepal, that the U-shaped valley in left bank we have measured and right bank also we have measured. See the U-shaped valley topography effect is clearly indicated that here it shows some north 20 degrees and in the left bank it is north 130 degrees. That means it is taking the shape of the valley. So this is very important parameter while conducting any stress measurements and all, any topography effect is there or not, like that we have to examine. So tunnel should be steel lined. I mean, I already minimum principal stress is also important parameter to avoid the maximum economical way. If you want to go for that, minimum principal stress in the rock mass falls below the maximum dynamic water pressure in the tunnel. It is applicable for unlined tunnels like HRT and other areas, head-raised tunnels and all the hydraulic projects and other areas. That minimum principal stress always should be more than the water pressure in the tunnel. Then only it will be stable. Otherwise, water leakages will be there. So this is the thumb rule. The minimum principal stress will play a vital role while designing the unlined tunnels. So this is the tunnel. And we have conducted in Himachal Pradesh one of the hydraulic projects in the valley. Away from the valley, how it is acting, section requiring how concrete lining is required or steel lining is required. That also we can suggest based on the measurements of the stress. So we have measured in either side of the valley, that valley type of one nala. So we have seen that one area, it is that we have given the direction and all, section where section requiring steel lining and where the section requiring only concrete lining is sufficient. That also water pressure, suppose sigma small h is greater than water pressure, then section requiring only concrete is sufficient. Suppose if water pressure is more than this sigma small h, that means minimum principal stress, then that requires steel lining. It is very much important parameter. So in the same way, like Kalakud and Kunnikud somewhere in one of the hydraulic projects, we have measured how the proposed HRT should align, how the stresses play the role in the cuts to orientation of the HRT. We have measured there also we have given the parameters according to our parameters only they have designed the HRT. So this suppose there are three type of stresses if you already explained. Regimes also you can see three type of regimes. Suppose if sigma V vertical stress is more than the horizontal stress, maximum principal horizontal stress, and maximum principal horizontal stress, small minimum principal horizontal stress means normal fault regime it is. That means wherever if you find out that sigma V is more than the sigma capital H means maximum principal stress, it comes under normal fault regime. Suppose if it is thrust fault regime means maximum principal stress is more than minimum and vertical, then it is called thrust fault regime. In strike slip fault regime, maximum principal stress is always greater than the vertical stress. Based on these principles, we have to find. We can find out the regimes also. According to regime, suppose if we some of the areas you can see in the ice hockey stadium in Norway, I think some area it is. The vertical stress is actually per 100 meters it should be 2.7, but the rock cover is only 40 meters like that. But they have constructed the ice hockey stadium in below the rock surface, 40 meters rock cover. But it is very stable. Why? That means the horizontal stress is more than the vertical stress. Why? How? Because Vertical stress is 40 means very, very less. Vertical rock burden is very, very less vertical stress, but it is stable because that is also one rule is there. In cumulative geological history, there was a big rock overburden. In the history of the time, it has been eroded and washed away, but still rock remembers that horizontal stress. So high horizontal stress they have noticed, and they have constructed the ice hockey stadium. It is very stable. So like that, in the suppose in force, axial planes always folds also define the greatest principal stress. The fold means if you keep the paper like this, if you press in two directions horizontally, automatically paper will bulge like a folds. That is a folds forms like that only. In dike, suppose if you see dike always spreads wherever the least resistance path, dike will spread. Where there is a least resistance path means that is the direction of maximum principal stress. Suppose if you find out the dike anywhere, that means if you measure also in that direction only, sigma capital H, that means maximum principal stress always concentrates. Suppose tectonic force, I told you horizontal compression force acting parallel to the surface of the earth, then the folds will be formed. Greatest stress axis is always horizontal. So in the faults, it is very, very advisable, already advised, whenever you make the stress measurements and all, it should be away from the fault. Because if you measure the stress near the fault means the redistribution because of the redistribution, stress will give the different result. That is called perturbed stress. So if you want to know the reason of stress, means local stress means you have to keep away the stress measurements from the fault. So we have measured in one of the coal mines in Tesgora in Nagpur area, Parashia area. So that near the stress, near the fault, we have measured the sigma capital H, that is 11.2 MPa, and sigma small h is 5.6 MPa. And orientation is not 30 degrees west. Suppose if away from the fault, but for someone SNT project, we have just done a lot of research in this area, and we have measured the stress. It is away from the fault. That means almost 200 meters away, 300 meters. Again, its sigma capital H is giving 9 MPa, and the direction is north 60 degrees west, surprisingly. That means fault always, if near the fault, stress will be perturbed. That will be, as stress will be redistributed. So you have to, whenever you want to measure the stress, you have to avoid the fault areas. Away from the fault only, testing site should be located. So effect of fault on in situ stress, if you model, it will be like this. So whenever there is a stress around underground opening, if you model that the stresses and all, these stresses and all will redistributed near the opening, stress will be like this, all these stresses and all. So you see this is the opening, and the stresses are concentrated like this, and away from this opening and all, if you measure, whenever you want to measure in any cavern, the excavation effect also will be there. That means 3 times of the diameter, 3 times of the diameter of the tunnel. Suppose somebody asked me in the exploratory drift to measure the stress, immediately I have to see what is the diameter of the tunnel. That is 3 meters or 5 meters. So 3 times, 2.5 to 3 times away from the diameter of the tunnel, size of the diameter, we have to measure the stress. That is, then only it will give the virgin stress. That means natural stress. Otherwise, excavation effect will be there. The stresses will be again different. That means you will get induced stress, not in situ stress. So roof collapse, how it is associated with the K, I already told you, horizontal to vertical stress ratio. If it is less, it will be roof fall, how it will be. And if it is more, how the roof fall will take place in the coal mines, one of the coal mines and all. This is the example. So what is the thumb rule? First of all, wherever there is a cavern, where is there is an underground powerhouse, where is there is a structure, underground structure, if you want to construct that orientation of the structure, orientation of the powerhouse or any cavern, the long axis of the cavern should be oriented towards the maximum principal stress direction only. This is the thumb rule. And otherwise, the deflection and all, if you total displacement and all, if you see how it will show the displacement and all, away from the this thing, any deviation from the orientation and all, the result will be like this. Distribution of institute surrounding rock mass and the deflection angle S max will be, after simulation, it will be like this. So in anacline fractures, you can see if it is alignment is through vertical, exactly. Maximum principal stress direction means that it will be like this. Fractures and all oriented will be like this. Some of the natural fractures and all. Otherwise, you can find out some of the unequivalent fractures and all. If you find out in any borehole, you can clearly, indirectly, you can measure. It is not according to the stress direction. It is away from the orientation of the maximum principal stress. Like you can have a small idea, rough idea about the stress. So if sigma capital H, the thumb rule I am telling, the third thumb rule is if sigma capital H is less than sigma V, the span should be more sufficient span you can have. That means capital H sigma maximum principal stress is more means the span can be more. If vertical stress is more, like this, if vertical stress is more, that means it should be constructed like this. Vertical stress, that means height of the roof can be more if vertical stress is more. It is sigma capital H is greater than sigma V, like this. So sigma capital H, if any deviation, how it is falling and all, collapse of the tunnel, it because we have seen the photographs on some of the areas and all, we have advised them to orient the tunnel according to our direction, but small deviation, some of the problems and all, they could not do. Afterwards, we have seen, after 3 months, 6 months, again, they have called us and we have seen this is the problem we have encountered. So some of the things you see, morning, Professor Mahendra Singh has just given an idea. He has explained about the Malpasset Dam disaster. Now everybody know that after disaster, Malpasset Dam disaster, many people died. We have done a lot of post-mortem studies. What is the use? Geologists blamed civil engineers blamed geologists. That's all. Blame game started for so many years. But whatever it may be the case, it is crime against humanity. Because if you cannot properly design the rock, cannot properly design the caverns and all, it will be a disaster. Unfortunately, in our India, very least importance is being given for the research purpose. For any suppose underground mines, coal mines and all, if you go, production is most important. Safety and all, okay, something and all they will do. If you suggest something and all, you should not stop the production. Production is the most important thing, and safety also okay. But if you tell, so these are the parameters required, first of all, they will ask why. Why it is it required? Is it necessary? Like that. Recently, I don't know, many people maybe in the Polavaram project in Rajahmundry, I have visited last March. They have called a CWC has given some guidelines to measure the in-situ stress directions in the navigation tunnel and irrigation tunnel. And they have called me and I have gone there and I just have seen the tunnel, everything. And I just suggested them, the formality parameters are most important. CWC already instructed you to go for this test, like that. They have agreed and I have reached Bangalore and I have sent the proposal. That is only an amount of peanuts, that is 35 lakhs. 35 lakhs, if you compare the total project cost, how it will be, it is nothing, not at all, 1% also, 0.001%. After that, even after 3 months, 6 months, people they are asking why it is required, sir. I don't understand, because people they are giving least importance, but the consequences, if you see afterwards, it is really irrevocable. We can't do anything. You see, this is where the roof is meeting with the floor, that the side walls are meeting with the floor, high horizontal stress. I told you that intermixing rock structures faces due to the high stress at the depth of 2,700 meters in one of the underground mine. This is a collapse of the side wall because this is not according to the orientation what we have proposed. This they have constructed. This is now they are facing the music. This is the problem. Now they have to rectify all the, because the high stability, for the stability and all, that is, they have to go for the redesign it, and they have to spend a lot of money. I think more than 100 to 200 crores extra they have to spend on this. So aftermath of the severe rock bursts also because of the stress only, rock bursts will be formed. So weak rocks under high stresses may lead to squeezing of ground conditions, which may result in damage to the ground support system or require the costly re-excavation of the tunnel section. This is in rock burst damage in Kolar gold fields. So this is the severe roof collapse in mines. This is also not according to the stress orientation. So reasons for the failure is, I told you, because we don't have that much knowledge, not sufficient knowledge about behavior of the rock. That means we are giving least importance. We are just studying the 1%, 2% only. Remaining things and all we are imagining. Okay, nothing will be happen unless something happens. So neglecting small observations, something small things also. I told you some anacline fractures you observed in the borehole and all these things. That means according to it is not according to the stress direction. And all these things one should have the imaginary power. That means one should forecast all these things. Then not sufficient familiarity with rock mechanics. One should study the rock mechanics properly, how to advise all these things. So how to measure the stress measurement techniques? So there are indicative methods and field-based methods and core-based methods. So in indicative methods, borehole breakouts and core disking. In field-based methods, water coring technique, hydrofracturing technique. In hydrofracturing technique, there is a classical method and HTPF method, and core-based method, strain recovery method, and Kaiser effect. All these things just briefly I will explain because we are lacking time. So this is the borehole breakout. This is the stress-induced compressive failure. That borehole breakout means stress-induced compressive failure. Suppose in the deep boreholes and all, extensive field evidence shows the laboratory experiments and all. The spanning was observed to occur at diametrically opposite by wherever there is a borehole breakout, the direction always it shows the minimum principal stress direction only. That is, it is not like maximum principal stress direction, because it is just breakout, it will form always in the direction of minimum principal stress direction. That if you find out any breakout in any borehole, that some calipers are there to measure that and all, any breakout and all, you can see immediately, you can come to know it is the towards minimum principal stress direction, the borehole breakout direction is concentrating like that. It is a thumb rule. And this is the breakdown. You see maximum principal stress opposite to maximum principal stress direction, the minimum principal stress. This direction only breakout always forms. So this is the breakout, how to measure and all. This is the naturally formed because some of the things are there. If you see the borehole televiewer, acoustic borehole televiewer, you will find out where exactly some of the borehole breakouts and all. You can caliper and all with help of calipers and all. You can measure. There is some. It will indicate only direction. It won't give you any magnitude or like that. But people are trying to find out what will be the intensity of that also. But maximum minimum principal stress direction, if you want to know, borehole breakouts are very much important. You can through breakout, you can measure. So breakout zone, this is the thing in in laboratory also we can measure. So core disking. What is core disking? In brittle rocks and all, if you observe in many areas in Himalayan areas, we have seen core disking takes place. The thinner the cores, the disking is there means higher the horizontal stress. Always some trough axis. Sometimes it is also some research is going on. The trough axis of the saddle-shaped core disks is extending aligned with the direction of maximum principal stress. That is the concept. Newly, people are doing research, a lot of research. Otherwise, wherever you go and see the core disking is taking place means there it is a horizontal stress is concentrating there. Like that, it is a thumb rule. There's some of the trough axis and our saddle shaped things are always there. That is very big subject again, which we don't have time to measure. That if you there's a thumb rule is if you have the thinner discs means higher horizontal stress, or the discs are not so thinner means that is low horizontal stress, and you can conclude. So this is the area where in a TISTA stage, I think TISTA hydraulic project, we have seen core disking and all, how we have seen. Even examined by some of the people scanning electron microscope also reveal set of lineations in the direction of maximum principal stress. So both the saddle shape and lineation markings on the surface of the core disc observed in scanning electron microscope. Unfortunately, we don't have that facility. We can find out the maximum principal stress direction also through core disking. So this war coring technique is very important technique. Many people they suggest for war coring technique. Of course, it is very tough exercise. We have done in many places. Now we have discontinued because you should have the expertise in drilling also. Otherwise, it is a futile exercise. So in this, we have to make a borehole, and second in the borehole again you have to make a pilot hole inside the borehole, and you have to install the deformation gauge inside or CSIRO hollow inclusion cell. And after that, after inclusion of that with the glue, and again you have to water core that portion where exactly that is the hollow inclusion cell is kept. You have to water core that, and afterwards you have to remove the water core, and you have to remove the core, and you have to measure the modulus of the Young's modulus of the rock mass. Then it will give the strain, and strain, you know already it is we will get the stress. This is the thing. Many people in Sweden and Finland area still they are following water coring technique. But only problem is if you just make a hole, and if you want to water core this portion, it won't align with the pilot hole. It will deviate. It will come towards some other area. It will go. If it is less than 10 meters means we can just measure. If it is more than 10 meters means this is a very big exercise, and it is not always, it is sometimes a failure thing. Many areas we have seen we could not complete properly because the pilot hole will not coincide with the main hole. That water coring and all will not come. Water core will not get the water. And if there is any water, the glue and all, it won't stick inside the pilot hole. That is also main disadvantage. So these are water core samples for biaxial test and all. Outside, inside, wherever you have measured the water coring and all, there only immediately you have to measure through biaxial test. You have to measure the rock with USBM gauge or CSR hollow inclusion cell, and you can determine the stress. This is also indirect method only, not direct method. Now you are calculating the strain, and after the strain, you are measuring the stress. So a water coring method is also, of course, it will give all three parameters: vertical stress, maximum principal stress, and minimum principal stress. I already told vertical stress is calculated, but in water coring method, vertical stress will be measured. That is the main. That means it is three-dimensional. Water coring always preferable, but only thing, it is having some disadvantages and all because of the glue and all. It properly should be placed and all. That water coring, the pilot hole and the water coring should be aligned properly. Otherwise, it will give wrong result. So flat jack method, many people know the flat jacks and all. There will be a jacks. The material with metal, the plates are there, and one hole will be there just to keep the oil, sufficient oil, hydraulic oil inside. And we have to prepare the slot in wherever you want to measure, and insert we have to make 2 pins, and afterwards you have to insert after 2 days or 1 day, you have to just insert the plate inside flat jack or 400 meters and 300 meters. And again, you have to grow. After grouting is everything is done, you have to potentiometers and LVDT kept and measure the distance. And again, you have to pump. If the original shape of the slot, it will, if you pump that rock, the 2 portions, they automatically, it will, the strain you can observe. The data through data acquisition system, that the slot grouted and all, it will retain its own position. That means you can measure the strains. In that way, you can measure the stress, but it gives only induced stress, not in situ stress, because you are measuring on the wall of the rock only just of 20 meters or 20 centimeters or 30 centimeters depth only. It gives induced stress. So this is also not useful for any design purpose. So these are the area where we have measured the flat jack test also, some of the areas long back. So hydraulic fracturing technique, this is the most important techniques. And there are 2 methods I already told you, classical method and HTPF method. HTPF method means hydraulic testing on pre-existing fractures. In the classical stress determination, hydrofracturing test is generally based on the assumptions, some of the assumptions we have. The pressurization occurs sufficiently fast to avoid the fracturing fluid, and the rock is homogeneous. The fracture initiates and propagates in a plane perpendicular to the least principal stress. That means after creating the fracture through hydrofracturing method, the fracture will be created always to the maximum principal stress direction only, that are perpendicular to least principal stress direction only. All these things break down pressure. If it is in a new fracture, you have to just create the fracture, or in HTPF method, if you want to create the fracture, you can create, or already existing fractures, you can reopen. That is the main advantage. You are having software and all, you have imported. Even you need not create the fracture also, already existing fractures and all, you can reopen. It also gives the stress. So these only have been utilized by Hubbard and Wills. they have initiated this fracture mechanics proposed by Rummel also. So this is the hydrofracture, how the fracture is created. This is the borehole, NX size borehole or EX size borehole. We have to drill in the vertical or horizontal or inclined direction. So there are, I will explain you, I will show you the equipment, how the fracture is created along the major principal stress direction. Plane of the created fracture, how it looks like this. It is shown here. So this HTPF method was coined by Cornett and Ballet in 1984. This is a three-dimensional, but only thing, if you want to measure by HTPF method, you have to select the zones wherever the rock is not fractured, and you have to increase the zones. Suppose 30 meters borehole, NX size borehole is there, or EX size borehole is there. Different zones you have to create. That means at 5 meters depth, you have to, the three measurements you have to do, and at 10 meters, 15 meters, 20 meters, 25 meters, like that. Maximum zones, that means you can get the maximum fractures. So standard deviation of all these fractures and all dip and strike we can measure, and afterwards this, even if you create new fracture also, old fractures also, we can HTPF method, we can measure the stress direction and magnitude. So this is the theory. Then now this is the equipment we are having. This is imported from Australia, from inflatable packers. I was trained under Professor Rummel when he was conducting the stress measurements in KGF long back in 95, 96. So we have imported equipment from Rummel also. And even I have given lecture in front of Cornett, who invented HTPF method in Finland in 2013. And they have surprised a lot of innovations you have done where we have not done like that. Because some of the practical problems we have encountered while doing this type of fracture testing of stress measurements. We have indigenously, we have developed some of the items and all, how to encounter all these things like that. So you see in the picture, this is the packer, it is called packer. This is steel reinforced rubber packers. This is the borehole. If inside the borehole, this packer should be inserted wherever you want to test the zone, test the know the stress. This is called injection unit. One hole is there. This is called hydrofrac tool also. So through this, there are two lines. One is for injection and one is for inflation of the packer. There are two hoses will be connected with this packer. Through one hose, you have to pump the water. So directly this water will go and get in the packer in the upward direction, in the lower direction. These two packers will be inflated. That means this packer will bulge. That means it will inflate. Afterwards, just it will catch, it will hold the whole borehole like that, upper direction and in downward direction also. So after that, once the packer is inflated, then you have to pump the water in some other hose, and directly this water will go to injection unit. And this here, with high pressure, water will come outside. So this water, whatever you are pumping and all, it can't go either upward direction or lower direction also, because already it is inflated. So what this water will do, it will create the fracture. It will create the fracture. So wherever there is a fracture is created means automatically you can come to know the PC, critical pressure, and refracture. Again, after that, you have to deflate the packers and all. Again, just you have to go inflate, and again you have to pump the packer, injection, and again it will create a refracturing. How much, what is the magnitude and all to find out. And shut-in pressure also we have to measure. 3 parameters: the fracture, dip, strike, and shut-in. 3 parameters we will get. Afterwards, you have to remove this packer, and again there will be an impression packer. That is impression packer. Again, you have to insert the same area where you have conducted. There you have to create, there you have to take the impression of the fracture you have already created. That impression will give the fracture already you have created, dip direction, and all these things, shut in and everything. So that with the we are having the software and all, we'll just see the how the fracture has been created, in which direction it is propagating and all. We'll find out the orientation and magnitude of the stress in that area, particular area. You see, this is the PC at critical pressure where fracture has already created, and this is PR refracturing. Already we have kept down. We have stopped pumping, and we wanted to try the pair, but it won't reach here. because already fracture has been created. So it is refrac. This is called PSA. This is called shut-in pressure, where you have to stop the pump. Then that means normal the water in the pump and the fracture in the water in the fracture, the both are equivalent. This is called shut-in pressure. That means normal stress across the fracture you have to measure. Like the 2-3 areas we have to measure, and we'll find out the shut-in pressure, fracture reopening pressure, and fracture initiation pressure, and all these parameters. You will just you will find out the orientation. This is called this is the packer, and this is the impression packer. So you see the impressions are like this. We have whatever we have created the fractures and all. We have taken the impression. The impressions will be like this, and we are having the software to address the fracture. Nowadays, in the deeper boreholes and all, after creating the fracture, again it is very difficult task to keep the impression packer and measure and take the impression of the impression packer, because in 600 meters means inserting the packer, it will take 2 days, 2 days time. So after creating the fracture, again you have to remove and you have to keep the impression packer, again it will take 5 days. Then impressions and all you won't catch. It is very difficult. So now acoustic borehole televiewer also we have taken, and first you pre-scan the borehole completely. Whatever the natural fractures and all you can delineate. You can come completely, you will have the clear picture. And afterwards, once you created the fracture with the hydrofracturing system, and afterwards again you run the scan, and with the BHTV, wherever you have created the fracture, automatically it will give a fracture impression and everything. This is the easiest method we are following in deeper boreholes. This is the images and all, where we have created fracture and all. Completely it will give the data, the stream, deep direction, and everything it will give azimuth. So this is the packer. This is the, I told you, the steel reinforced rubber packers, and this is very costly. The straddle packer nowadays it is costing around 23 lakhs. So we have to carefully insert in the borehole. Something happens automatically. Sometimes it won't come also. After inflating, after creation fracture, it won't come in the outside. So there will be a buoyancy effect and all. We have to carefully see. It is very difficult task. So we have conducted in the 600 meters depth of the Singareni collieries. This is the first time in India with our technology. Of course, we have imported for the equipment, but completely based on our technology, our knowledge, we have measured the stress measurements. Now we are going up to the 1000 meters also in some other areas. So these are some of the pictures. So core-based method, strain recovery method, just a small acoustic emission method. Suppose a rock is there, it should the stress should exceed already applied stress. Something will be there. If you apply more than already applied stress, it will occur. The emissions will be given. Emissions will be observed. That is called acoustic emissions. Through that is called Kaiser effect. Through acoustic emissions, you can just find out the magnitude of the stress. So Kaiser is a phenomenon observed in geology that describes a pattern of acoustic emission that repeated cycles, mechanical stress, and the absence of acoustic emission are seismic events until that load is exceeded. That means it should rock ko thappad mara. Just it won't recognize. Rock, of course, it is a dumb creature. It can't speak, but it will remember what is the stress already applied on that. If you exceed the already applied stress on that, it will forget the old applied stress, and the new stress it will remember. That only it is called, roughly, crudely I'm telling, it is called Kaiser effect. Through Kaiser effect, you can measure the magnitude of the stress. This is some of the areas, papers, and what we have done, the measurements and all, some of the areas and all, it has come in the media. These are all these things. So ultimately conclusion, thumb rules I already told. Opportunities we have to see economically how to go about, rock behavior, how it is changing, how stress is changing, maximum risk if not study the behavior of the rock mass, maximum risk we have to face, and maximum principal stress direction. Always it is a very important factor, and it is a key factor. In one of the examples I will tell you in the Gujarat also, Machu Dam, something I remember, if I correctly remember, in 1979, this is the same disaster like Malpasset Dam and Vizont Dam like that in Italy. So ultimately, they have studied 2, 3, 4 years, and they have written the report in Wikipedia. Also, you can see Machu Dam. If you open, it will show it act of God, or you blame the rock. Both can't speak. Even God can't speak, and the rock also can't speak. It shows the peaks of human arrogancy. So we should avoid that. and we have to handle properly the rock. Rock will respond to you properly. Unless you handle properly the rock will it show its true colors, and one day it will become a disaster. So my advice is always, irrespective of the cost and all, one should go data bank. One should have the data bank for the stress measurements and deformity measurements and shear strength parameter, shear stress and all. There's angle of internal friction and cohesion wherever the dam is constructed. All these parameters are very important. We are having all the facilities and all. My contact number is this. You can find out from the organizers also. My mail ID. These are the facilities we are having in NIRM. Institute stress by hydraulic fracturing method and wire coring method. Institute deformity also we can measure, plate load method, plate jacking method, or Goodman jack method and dilatometer method. And institute shear, direct shear method we can measure, and safe bearing capacity and modulus of subgrade reaction of the soil or rock, plate load test, foot load test, and standard penetration test. And we are having acoustic borehole televiewer also. All these facilities we are having in NIRM. So thank you very much for giving me the opportunity for today's lecture. Thank you.
Thank you, Dr. D.S. Subramaniam, for making an excellent and detailed presentation. May I request to the participants, if they have any questions, they may ask directly to the speaker. Participant can ask the questions if they have any. I think the concept has already been very much clear to all. Everything has been taught in detail. If the participants still have any questions, query, they may write to us directly. We will arrange the answer and revert back to you over the individual email IDs.
Thank you once again for giving me the opportunity.
Thank you, sir. Thank you for sparing your valuable time for conducting this session. Thank you all. Thank you to all the speakers and all the participants. See you tomorrow at 1100 hours for day 2 session. Thank you for the day. Stay safe, stay healthy. Goodbye.
Thank you.
Okay, thanks a lot.